Good evening, students of class 12. Let us continue the chapter number 3 with the topic resistance. Today we shall derive a relationship between the resistance and its dimensions and also understand the connected topics like resistivity and conductivity. I am Dhanu Saraiya. Keep watching this video till the end so that you understand these concepts very clearly. Fine? Now let us derive a relationship between the resistance of a conductor and its dimension. So for that let us consider a slab of length L and cross section area A. Let V be the potential difference between the two surfaces, that is the cross sections of the slab, and I be the current flowing through the slab. Then according to Ohm's law, we have the resistance R is equal to V upon I in this slab. Fine? Okay. So now let us make a variation in which we double the length of the slab. Make it from L to 2L. So I am considering that the slab length is doubled from L to 12, in which I have placed another slab which is identical to this slab number 1, such that the total length is now L plus L 12, and the cross section area at its ends remain the same as A. So we have L dash is equal to 2L, and we also have the potentials of each slab as V. Why? Because the two slabs are identical to each other. We have the potential differences for the slab 1 and the slab 2 same as V, such that we get the potential difference for this arrangement between the surfaces of the new slab as 2V, V plus V, 2V. Now, as you can see, the slabs are attached, so the current flowing through the slabs will be same as I. So, I dash, that is the new current, is same as the old current, I. Now, for this new arrangement, let us find out the resistance. That is R dash is equal to V dash upon I dash. What is V dash here? 2V. What is I dash here? I. But V upon I is R. So we get 2R. So our result is the resistance in this arrangement is doubled when the length is doubled. So the conclusion for this arrangement becomes R proportional to L. Resistance is proportional to the length of the conductor. You increase the length of the conductor, resistance will increase. Fine? Okay. Now let us consider the arrangement number 3, in which I am placing a slab of the same length, that is L, but the cross section area is A by 2 of each slab, 1 and 2, length remaining the same. Fine? Length remaining the same. So for this new arrangement, L remains the same, but area A dash is A by 2 compared to the original slab 1. Fine? Okay, so that means we have halved the area. Area is reduced. Fine? In this case, what is the potential through each slab? It will remain the same because the ends are same. For the slab 1, the surfaces are same, and the slab 2 also the surfaces are arranged at same points. So if points are same, the potential difference remains the same. So V dash is V itself, just like the original slab. Now, what is I dash? Is it the same for each slab? No. We have placed the slabs one above the other. So the current which was I now is distributed into I by 2 in each slab. Therefore, we get a resistance, say R double dash. Okay, we can give other name also. R double dash is equal to V. We can put here double here, double here. So V double dash upon I double dash. What is V double dash? Same V. What is I double dash? I by 2. I upon 2. So what has happened? We get 2V upon I. But V upon I is R. So what do we get? 2R. So what is our result now? R double dash, that is the new resistance for this arrangement, is doubled the original resistance. Fine. So when the area is half, resistance is doubled. So what is the conclusion here? The conclusion here is the resistance is inversely proportional to area. Okay? In the case 2, resistance is directly proportional to the length. That is, say, proportionality number 1. When the area of the cross section is halved, the resistance is doubled. What is the conclusion? That resistance is inversely proportional to the area. Fine. Let us consider this as 2. Equation number 2. So now combining the proportionalities 1 and 2, or the equations 1 and 2, we get R resistance directly proportional to the length, inversely proportional to A. That is R directly proportional to L upon A. We can write it as R is equal to rho L upon A, where rho is a constant called the resistivity of the material of the conductor. Its unit is ohm meter. Fine. So we have derived a relation to understand that resistance depends upon the material of the conductor, that is resistivity. It also depends on its dimensions, that is its length and area. Directly proportional to length, inversely proportional to area. Again and again I am saying this because depending on this relation, numericals are asked. The length is doubled, area is halved, or area is doubled. Accordingly, the resistance will change and hence the current. Fine. So keep this relation very clearly in the mind so that numericals on this concept can be solved by you very easily. I hope you have understood this concept that the resistance depends on the dimension of the conductor as well as the material of the conductor. Okay, so take a pick. I shall move, and I hope this particular concept is understood by you very clearly. In the next page, we shall understand the relationship of rho, that is resistivity, and conductivity and current density. So keep watching this video till the end. Now let us continue this video with the same topic of resistance, resistivity, current density and conductivity. They are all connected to each other, and how are they connected or how are they related? Let us see and let us derive. So first let us define current density. Current density is defined as current per cross section area. Fine. Okay. Now from the Ohm's law we have learnt V is equal to IR. In the previous page we have learned R is equal to rho L upon A, which I have just substituted. Fine. Such that we get V is equal to I upon A rho L. But this I upon A as written here is current density. V is equal to, therefore V is equal to J rho L. Fine. Okay. Where J is the current density and whose unit is ampere per meter square. So this is one relationship where the potential difference between the ends of a conductor is given as J rho L. Now in the previous chapter number 2, we have learned that the potential difference between the cross sections of a conductor, two ends, is equal to EL, where E is the electric field given to the conductor such that there is a flow of electrons and L is the length of the conductor. Substituting this value or this expression in equation number 1, which we have derived just now, we get EL is equal to J rho L. L cancelling, we get E is equal to J rho. Or we can also write the vector form as E vector is equal to J vector rho, where J is the current density of the conductor and rho is the resistivity of the material of the conductor. Fine. Okay. So this is another equation number 2. Now here let us introduce the reciprocal of resistivity, which is called as conductivity, sigma. Sigma is equal to 1 upon rho, or rho is equal to 1 upon sigma, where sigma is the conductivity of the conductor. Okay, and its unit is ohm inverse, meter inverse. Fine. Now let us substitute rho is equal to 1 upon sigma, that is resistivity is reciprocal of conductivity, in the equation number 2, such that we get E is equal to J vector. Instead of rho, let us put sigma, 1 upon sigma, such that we get J is equal to sigma E. This is another relationship which we will be using in the next parts of this chapter. Fine. Okay. So here we have derived 3 equations, that is V is equal to J rho L, that is potential difference is equal to J rho L, E electric field given to the conductor is J rho, and J is equal to sigma E. Fine. So remember that rho as well as sigma both are constant. Here also rho is a constant. So it is understood that E is proportional to J, V is proportional to both J and L. Fine. Here J proportional to E. All these small proportionalities have to be remembered by you such that you can use them in the numericals and the resolving questions, application questions. Fine. Very important is you have to understand the proportionalities. They can ask you numericals by doubling the length, by doubling J, doubling V, what happens to J. All such variations can be done using these proportionalities. Fine. Okay. So I hope this concept and formulas are jotted by you, remembered by you to use them in the application questions. I move so that you take a pic of these formulas and remember them for your further applications.